So our first panel participant is a professor of physics at Princeton University. In addition to his studies of gravitational collapse, black hole mergers, and cosmic singularities, he designs algorithms to efficiently solve Einstein equations on large computer clusters. Please welcome Frans Pretorius. The next participant is an assistant professor in the Gravitational Waves Physics and Astronomy Center of California State University, Fullerton. She has developed a widely used model for dense matter inside neutron stars. She is the senior lead on the extreme matter group within the LIGO scientific collaboration. Please welcome Jocelyn Reed. Also joining us is the lead astrophysicist in the LIGO scientific collaboration. She directs the Center for Interdisciplinary Exploration and Research in Astrophysics at Northwestern University, where she is the Distinguished Professor of Physics and Astronomy. Please welcome Vicky Kalogera. And our final participant this morning is a professor of physics at Syracuse University, whose research involves using gravitational waves observations to understand the nature of the universe. Please welcome Duncan Brown. You know, suppose that somebody from some alien civilization, very advanced civilization, comes to Earth and asks us, how good are you? What have you achieved? Then one very good way to answer them would be, we have detected gravitational waves from merging black holes and neutron stars. And the reason that this would summarize in an extraordinarily good way our achievements is that, number one, on the theoretical side, it would tell these people that we have reached a situation where we understand already that space-time is not just the backdrop of cosmic events, as was once thought, but is actually an active participant. And space-time can stretch, it can curve and warp, and that gravity is not, we also understood that gravity is not some mysterious force acting across distances in space, but rather it is an expression of the curvature of space-time. So the sun, you know, as if it's standing on a trampoline or something, it's warping space, and then the planets find the shortest paths in that curved space. That's what gravity is all about. So this is on the theoretical side. Then on the experimental side, the fact that we have detected these gravitational waves will tell this alien civilization that we have reached such a level of technology that we are able to detect displacements that are thousands of times smaller than the size of the proton, which is really astounding when you think of this. So with this one sentence, we have detected gravitational waves from merging black holes. We would tell these civilizations where we have reached. So let me start with Frans. And we could say, I will make this statement and you will tell me if I'm right, that by the LIGO discovery of gravitational waves from merging black holes, this actually was the very first direct discovery of an Einstein black hole. Am I right?
Yes, I agree. And it's actually the history of black holes is fascinating. You know, as probably most people here know, Einstein, you know, he came up with a theory of general relativity finally after many years in 1915. And within a few months, Karl Schwarzschild discovered the first black hole solution, the first theoretical solution that describes what we know of as black holes today. And no one took that seriously. It was such an absurd solution. It predicted so many things that people couldn't understand. Even Einstein thought it was just a mathematical oddity. And then in the 60s and 70s, though, when perhaps what several people, including Kip Thorne, call the golden age of black hole physics, theoreticians finally sort of got an understanding what the solution represents. And yes, there are a lot of bizarre things about it, but we sort of understood it that it's actually perhaps not quite as strange as what people thought. And then astronomers also discovered various objects in the universe which was very mystifying if they weren't black holes.
They were good candidates.
Good candidates. But then it's sort of a strange thing happening. If you think like the doubt that was there in the scientific community about black holes, then from the 60s and the 70s when these objects started to be discovered, it almost went completely the opposite. That black holes became this thing which almost had to be there. It was almost, what else could there be out there? But if you think about it, until this LIGO discovery, what scientific evidence that we actually have that there really are black holes as described by Einstein's theory?
And by that you mean really this extreme warping of space-time.
Right, the extreme warping of space. So in the sense that, so what the evidence that there was before was that, I'd say there was incontrovertible evidence that there were very dense, compact, massive objects out there. But that there was no direct evidence that they were black holes of general relativity. In other words, these manifestations of space and time, where space and time is so warped that event horizons formed. But then with LIGO's discovery, we saw the gravitational waves coming from this warping of space-time around two merging black holes. To me, that was the most astonishing thing about seeing that data for the first time, is it was the first direct evidence for black holes as described by the theory of relativity.
Right. Just to continue on the trampoline example, and black holes, they warp the thing so extremely that they all essentially punch a hole through the trampoline. So this was the evidence for that. Jocelyn, neutron stars are extraordinarily dense objects. In fact, 1 cubic inch of neutron star matter has a mass of maybe 1 billion tons or thereabouts. Now you take such two neutron stars and collide them. So it's a little bit like an accelerator experiment, only on a cosmic scale. Tell us a little bit about that.
Yeah, so neutron stars are the remnants left over after massive stars, not quite massive enough to collapse to a black hole, reach the end of their lives, and they compact down into the core of the star is more than the mass of the sun, about 1.5 times the mass of our sun, but compacts down into a region about the size of Manhattan. So it's this phenomenally dense object. And one of the interesting things about these dense objects is that we don't exactly know what happens at their cores. So the matter in neutron stars is denser than any physical matter you might be familiar with, so dense that we don't anymore have nuclei with electrons kind of fuzzing around them, but the nuclei have been compressed so close together that a neutron star is almost like an atomic nucleus the size of a city.
Let me just stop you for 1 second. So basically, if you take a normal atom, the size of the atom is about 100,000 times bigger than the size of the nucleus. But in this case, you have compressed everything so much that the nuclei touch each other. There is no more that space of 100,000 times. Please go on.
Yeah, so we have this bizarre form of matter, and it's possible when we get to these densities, we're still describing standard model physics, but we don't understand how to translate that into what happens. And it might not be that there are protons and neutrons like nuclei anymore, but there are just direct quark matter interacting with itself in ways that we can't create and reproduce in any terrestrial laboratory. So these cosmic accelerators smash neutron stars together. They take some of the densest matter, and the gravitational waves trace out the dynamics of this collision, and then they collide and they throw out the source of an array of electromagnetic counterpart observations in this really dramatic kind of event that we've now for the first time observed. So we see the traces of the densest stable objects in the universe in this panoply of observations.
Quarks, just for those who don't know, are the fundamental particles that make up protons, for example. There are 3 quarks that make up a proton and so on. And in this case, you really reach those densities where the quarks interact, with each other and so on. Vicky, so we're talking about collisions of black holes, of neutron stars and this. But how do these systems form at all? How do we get to this situation which, then we have something to collide?
Well, theoretical astrophysicists have ideas about how these systems form, but we don't have the perfect answer to your question. So over the years, we have developed some hypothesis for how this can happen in nature. What we know for sure is that it happens in nature. We know that these binary systems, 2 black holes in orbit one around the other, just like the Earth is going around the sun, but now imagine 2 black holes, or 2 neutron stars, like as dense as Jocelyn was describing, in orbit one around the other, exist in nature. And the way they might form is there are 2 classes of potential formation mechanisms. One is you take 2 stars that are formed, they are born in pairs. They are born one going around the other, unlike our sun, which is a single star, as we know.
Yeah, but about 50% or so of all stars are in such pairs.
Binaries, exactly. So we know from observations with regular telescopes that most of the stars out there actually are born in pairs. So they are born in pairs, and they start burning the nuclear fuel. They're producing light. They're going to go through the nuclear evolution. Eventually, their cores are going to collapse. And depending on their mass, if they're extremely massive, 20, 30, 50 times the mass of the sun, then they're going to form black holes. If they're lucky enough, then at the time of the formation, the 2 black holes will stay in orbit, and the system will not disrupt. And then you're going to get a binary. Or you might get a binary with 2 neutron stars. And then eventually, they're going to come together in this spiral dance. They're going to keep going one around the other, emitting gravitational waves, which now we have detected. And then they have no other option but to collide together. So this can happen with black holes or neutron stars. There's a whole other class of formation channels that, broadly speaking, can be described in the following way. You can be in an extremely dense stellar region, not the kind of region we live in, thankfully. Otherwise, we wouldn't have a quiet planet like we have it. But there are parts of the galaxy where stars are extremely packed together in a small volume. So you have a collection of stars. We call them clusters of stars. And the stars may be individual stars, and they're going to go through their nuclear evolution, and eventually they're going to form the death remnants, neutron stars or black holes. Those, especially the black holes, are going to end up being the heaviest objects in that cluster. And as imagine, I guess, in a glass of, I don't know, I'm thinking a glass of milk with heavy, I don't know, chocolate.
The heavy stuff
coffee,
sinks to the bottom.
I'm thinking of coffee beans covered with chocolate. I don't know what I'm thinking about this. So they're going to sink in the bottom because they're the heaviest things. And as they sink in the bottom, they're also moving at high velocity, and they're interacting together. And they can actually, even though the black holes were formed separately, they can actually combine together into pairs. And then eventually, with the emission of gravitational waves, they're going to end up colliding. Right. So you have pairs that were born as stars together, and they stayed together all their lives, and others that went through the dance floor. They had many partners along the time of their lifetime, and eventually they collided with some partner.
Let me just add one thing to both of their comments, and that is, I mean, they both describe stellar evolution. And in stellar evolution, stars basically spend their lives trying to fight gravity. If you don't have any opposing force, everything, because of gravity, will collapse to the center. So stars spend their life trying to fight gravity, and they do that by doing nuclear reactions that produce a lot of energy, and which builds a lot of pressure, and that holds them against gravity. But as they go through their nuclear fuels, at some point they run out of fuels. And then gravity finally has the upper hand, and that leads it eventually to this collapse, which forms neutron stars or black holes. Duncan, I said that experimentally, you are the closest from this group to the experimental side. What does LIGO do, and how does it do it?
Sure. So LIGO is basically a very, very precise ruler for measuring length. And to give you an idea of how precise, think about you have these two black holes or neutron stars going around each other, many, many, many billions of light years away, producing these ripples in space-time. And the physical effect of these ripples in space-time is to stretch and squeeze space itself. So gravitational waves, weak gravitational waves are probably passing through this room right now, stretching and squeezing everything in this room. But they're so tiny that we don't notice. Fortunately for us, there's no nearby binaries producing gravitational waves that you would feel. Otherwise, we don't live on a quiet planet. So the stretching and squeezing. So you gave an analogy that over a couple of miles, you're measuring a distance that is a change in distance that is less than the size of a proton. Or another way of saying that, if you think about the distance between the sun and the nearest star to the sun, which is about 4 light years or so, you're measuring that distance to the width of a human hair. So that's how precise the measurement has to be to detect these incredibly weak gravitational waves. And so LIGO itself is both simple and complicated. It's simple in the sense that it's an experiment that you can build as an undergraduate in the lab. You take a laser beam, you shine it through a mirror that's partially silvered, and so half of the laser beam goes this way and half of the laser beam goes the other way. You put another mirror at the end, another mirror at this end in this L shape. You bounce the light back, so the light comes back towards what we call the beam splitter, this mirror that split the beam. And then the light leaks out towards a light detector here, a photo detector right here. And if you set this up so the lengths of those two arms are perfectly balanced, then you can set it up so in LIGO, classically we think of light as a wave, and you set this up so the peaks and troughs of the waves line up, and so you get what we call constructive interference coming back towards the laser and destructive interference going towards the photodetector.
So constructive interference is when the light from the two things amplifies each other, and destructive is when it kills each other.
Right.
Yep.
And so all the light comes back towards the laser when the thing is perfectly balanced. As a gravitational wave passes through, it stretches one arm and squeezes the other arm, and so it upsets that perfect length balance between these two arms. Now, in reality, these arms are 2.5 miles long, with 40-kilogram mirrors at the end of each arm. So as a gravitational wave goes past, it changes this delicate balance of the two arm lengths, and some light just leaks out towards this photodetector. And that light, the light that's leaking out towards the photodetector, encodes the length change, which encodes the ripples in space-time, which are the gravitational wave signal.
They have these things with miles-long arms, and they measure the thing changing by the length of a proton. I mean, this is the experiment. This is why I said, if you tell somebody we have achieved this, there is nothing more dramatic that you can say that we have achieved from a technological perspective.
It is, Mario, it is actually the most precise measurement we've ever made, humans, in any field of science and technology.
Yes.
And I think coming back to a question to Frans of, have we directly detected black holes? I think everyone believes there was firm evidence for black holes from observing the light given off as material falls into black holes, or the light given off by stars orbiting black holes. But with LIGO, those gravitational waves, those ripples in space, came from the black holes themselves. So this machine reached out and touched the event horizon of those black holes with a machine that we built here on Earth.
Right. So, Frans, we've now talked a little bit about how these things emit gravitational waves and whatnot and so on. And these are these perturbation in space-time. Tell us a little bit about that, and also tell us a little bit about how do you simulate what happens in these things.
Right. So I guess as people have spoken about in Duncan, so these gravitational waves are ripples in space and time. So Einstein's theory of general relativity is not a theory about a force of gravity. It's a theory about space and time. And it says that space and time, or space-time, can be described by a geometric structure. Distances by things separated by a certain amount of space, or distances in time. We're moving in time as we speak now. And what
Too
Einstein
fast, unfortunately.
Indeed.
And what Einstein theory says, so like what Mario described in the beginning, if you sort of think something like the Earth or the Sun is producing this bent sheet, which sort of represents the curvature of space-time. But when objects accelerate when they move, and one example of acceleration is two black holes or two stars orbiting each other, or the Earth going around the Sun, we're actually producing gravitational waves right now. But that kind of acceleration produces these little ripples in the geometry of space and time. They propagate out at the speed of light, and as Duncan was mentioned, the exact details of the shapes of these ripples encodes what produced them. So you can imagine just two things going around like that produces a very nice sinusoidal pattern in the wave.
Let me just stop you for 1 second. One of the things about Einstein's theory is that gravity doesn't act instantaneously. It propagates at the speed of light. So these disturbances propagate at the speed of light. That is a very important feature of Einstein's general relativity. Please go on.
Okay. So that perhaps brings to one problem with something like LIGO, in the sense that, as what Duncan described, it's not a telescope. It's not focusing gravitational waves onto an image so we can sort of see what things look like in gravitational waves. Perhaps a better analog is like a seismometer. There's something that produces an earthquake in space and time. These ripples propagate, and LIGO measures these little fluctuations. So now we say, okay, we've seen some ripple. What does that mean? What does it represent? How can we say that it's two black holes that collided, or it's two neutron stars that are collided? And the way that we do that is we try to solve the Einstein equations using various theoretical tools, pencil and paper methods, computer simulations, and try to predict what Einstein's theory says for each one of these systems and vary the parameters of the system. And then for the events that LIGO saw, we take these waveforms, these little ripples, and we try to match them up to our various predictions. And when we get good matches, we can say, the parameters that went to the simulations, that is how we interpret the ripples.
Maybe we can have the video. And so here you have these two objects, and they spiral around each other, and you can see that they are getting closer and closer. And they emit these ripples, which are these gravitational waves. And the frequency of the waves becomes higher and higher the closer they get together. And eventually, boom, they merge together. And in the case of neutron stars, they produce this thing, which we happen to call a kilonova, simply because it's about 1,000 times brighter than what we call a normal nova. And basically, that's what we have seen. So please go on.
The problem with these simulations, the Einstein equations are very, very complicated. And well, that's perfect for computers. They don't care about complication, except it just takes a lot of processing power, a lot of computers. So for example, to do an actual simulation like something like that, which lasts for perhaps a few dozen orbits, the merger calculates how the gravitational waves propagate, it might take anywhere from, say, 100,000 to a few million CPU hours. So your typical, like the power in your cell phone, and these days cell phones are very, very powerful. So don't try this at home.
Yeah.
So if you had like 1 million cell phones all working together for an hour, they'd be able to produce one waveform.
Right. Can you just address this? I mean, there is this thing that is known as the chirp.
Yeah, so let me explain. So I said, like, the structure of that signal tells us sort of what's going on. And for binary black holes, it's called this chirp waveform. And so what's happening is, so now we've got these two black holes that are in orbit. So when they're pretty far apart, it's a very nice, essentially circular orbit. And I said, we get sort of a sinusoidal wave. And you can actually also, it's nice with these black hole mergers because the frequency that they're emitting at, it is in the audio range. So you can almost, you can say LIGO's listening to the sounds of the universe. So say two black holes, they're orbiting at a certain frequency. So it's when they're far apart, it's essentially a monotonic frequency, so just a very pure tone. But this orbital motion produces gravitational waves, and that drains energy from the system. And so that's why two black holes that are in orbit, they're not going to stay in orbit because they're losing energy to gravitational waves. And the way that affects the system is that they start getting more bound. They start moving. They spiral in closer to each other. So when they're closer to each other, They have to go faster in some sense. Now there's a stronger, if you will, gravitational force, so they have to start moving faster. So the sine wave that they're emitting increases in frequency, so the period decreases, and it also increases in amplitude because they're going faster. But now they're going faster, so they emit more gravitational wave energy.
So the sound is stronger, but the pitch is higher.
Right. So it's sort of there's this runaway process, and so they start spiraling around faster and faster and faster, and eventually they collide. And so if you think of like what happens to this monotonic, well, almost monotonic wave that's increasing in amplitude and frequency, and it's this whoop sound. It's like that's what's called a chirp. And then finally, when they collide together, there's that final burst of the chirp. And then very, very quickly, in fact, astonishingly quickly, the two black holes emerge into a single larger black hole, and it settles down to a stationary black hole that's completely quiet. It doesn't emit gravitational waves. And that final stage is called the ring down phase. And you can almost think of it's like these two black holes, they're busy chirping because of the motion. They smash together. It's like having taken a bell and like giving it a big sort of, you hit it with a hammer. Now, bells are very efficient at ringing. They make a good sound for a long time. Black holes are terrible bells. It's like throwing two pieces of putty together. They almost stop ringing immediately, which is actually an astonishing prediction. Like, how can objects stop ringing that quickly? But black holes are like that.
Thank you. Now, Jocelyn, I want to ask you something, but I'll just make a small introduction to my question so that it will become clear. So, for example, on Earth, we have tides. And the tides are because of the moon. Basically, what happens is that the point that is closest to the moon feels a little bit of a stronger gravity than the center of the Earth, and so the sea goes a little bit higher. Similar thing happens at the farthest from the moon point, because there it's the center of the Earth that moves a little bit further, so still the sea is higher. Now, believe it or not, these two neutron stars, even though they have a mass a little bit larger than the sun, but they're just 6 miles, in radius, they still, when they get very close, they can raise tides like this. So tell us a little bit about this, and how can we tell whether there are tides or not?
Yeah, so as Frans said, so the gravitational wave is draining energy from the system, and that's changing how the orbit happens, and then slowly as the stars get closer and closer together, different features of the stars come into play in the dynamics of how they're orbiting. So when they're far apart, the only thing that really matters is their mass. Depending on the mass of the star, they'll orbit at a particular frequency, and the frequency changes in a particular way. As they get closer, the influences of their spins and how different the mass is starts to come into play. And then as they get very close to each other, the stars' tides become more and more significant. And what happens is, in addition to energy being drained away by the gravitational waves, some of that energy goes into deforming the star. So you can think of a star at rest has a certain energy, and to deform the star, to raise the tides, that changes the energy. It pulls the star out of equilibrium, and that takes energy to do. So the forming the tides is another drain on energy, and so it causes the in-spiral to accelerate. And then, of course, there's also a factor that depending on the size of the star, they eventually crash into each other. And if they're very compact, they can do a few extra orbits. If they're large, they'll interfere with each other more quickly. So the chirp at the very end, the pattern of the ripples will either get accelerated by tides and then cut off by the stars smashing together, or if the stars are very compact, the tides are weaker. It's harder to disrupt a very compact star than a larger, fluffier star. So the more compact stars will continue their black hole-like orbit and then eventually merge in a more simplified way. So that's encoded in the pattern.
Right. So basically, how much you can deform the star by these tides depends on well, we call this the equation of state. Basically, it depends on how hard it is to deform it. How, how does it respond to trying to change, by applying a force to it, how trying to change that. So basically, isn't it true that what happens is that these tides, at some level, tell us this equation of state? I mean, how the pressure depends on the density of the star and so on.
Right. So we're trying to find out what are the properties of the mysterious matter in the core of the stars. And the key property that we're interested in is at a given density, how much pressure does that matter provide? So this is matter's last stand against the crush of gravity. So it has to be providing a lot of pressure at a very high density. But if that pressure is low, the collapse happens a little further and you have a compact star. If the pressure is high, you have a larger star. And the larger the star is, the larger the impact of the tides. The outer material of the star is farther away and it's easier to be disturbed by the tidal force of the other star. So a larger star deforms more, pulls more energy from the system.
Vicky, we mentioned this a little bit, but I want to get a little bit into the more nitty-gritty. Black holes are, you should understand that black holes are actually very simple objects. They are characterized by two numbers. Well, three in principle, but one is the mass, the second is the spin, how fast they rotate, and the third in principle is their electric charge. But in astrophysical objects, there is no real electric charge. So it's two numbers, basically. But from these things, we can try to determine the mass and the spin, and also the orientation of the spin, namely, is it rotating around this axis or that axis, and so on. Well, and also things like the distance and things like that. Walk us a little bit through how do you determine all these parameters from the observations?
Yes. So it goes back to what I think Frans mentioned it first, the chirp, okay? So all this information about the mass and the spin and the distance of the source of these death spiral dances and eventual collisions, and the tides, they're all encoded in that chirp that we're observing with the gravitational wave detectors. What we measure directly is basically the squeezing and stretching and squeezing and stretching of the space-time here on Earth, which is the propagation of the wave that started from the source. When the wave is reaching us, it's disturbing our space-time here. And what we measure is the amplitude of the wave. We measure the frequency of the wave. And we also measure the duration of the wave. And during that duration of the signal, the frequency is not steady, but it actually changes. So we can measure what we call a frequency derivative. So the frequency of the wave is not a simple sinusoid, as you were saying, but the peaks of the sinusoid are coming closer and closer together.
The rate of change
of the
wave.
Of the frequency is changing, and we can measure the rate with which the frequency is changing. So we have amplitude, frequency, and frequency derivative. So the rate of change of the frequency. So these three are the fundamental measurements we make, and we can use these three fundamental properties with a little bit extra information that is hard to get into right now. But these are the three main things that allow us to decode masses, spins, and the distance, because the amplitude of the wave is telling us something about how far away is the source and also how massive the objects are. And the change of the amplitude with time and the change of the frequency with time is also telling us something about the spins. Sometimes, not always. Sometimes we can constrain the spins, but sometimes we get very weak constraints on the spins.
Maybe we can have an image just so, in the case of the neutron stars in particular, we also observe this in ultraviolet light, optical light, and so on. And we have an image of what was actually observed with the Swift experiment. So look in that box, and you will see that thing which suddenly, well, you see it appear disappearing. It's in a galaxy that's, well, has a telephone number of 4993 and so on. But just realize that everything they told you, these are things that happen sometimes billions of light years away. So this is the type of thing we see. And it is from that type of information that you get all these details that you see here. And that leads me to you, Duncan, because in this case of the neutron star merger, there was somewhat of a mishap in that in one of, you see, they have this alert system where when something happened, because they want to alert other telescopes and this and that. When this neutron star merger happened, the alert worked in one of the locations, but not in the other. Tell us a little bit of what happened then.
That's right. So to set the context, as Frans said, gravitational wave detectors are like listening to the universe. You're listening to the sounds of space-time, the ripples. And gravitational wave detectors don't just look in one direction, they look in all different directions. So just like my ears can hear sounds from all over this room, if someone over there made a noise, then I could say, okay, my brain can localize that the sound is coming from over there, and I can point my eyes, and I can look over there, and I can see what's going on. And that's what we wanted to do with gravitational wave detectors and electromagnetic telescopes. We wanted to say, let's listen out for a gravitational wave signal coming from somewhere on the sky, somewhere out there in the universe, and then when we hear this signal in gravitational waves, to then say, point telescopes over there and look over there and see if you can see light in all its different forms coming from these two objects colliding. So we had a system that was set up that would alert us to these gravitational wave detections. And in order to figure out where sounds are coming from, I have 2 ears and a very complicated signal processing unit inside my head, so I can detect and I can localize sources. With gravitational wave detectors, we have 3 detectors. There's the 2 US LIGO detectors, one in Washington State, one in Livingston. And then there's a French-Italian detector just outside Pisa in Italy. So these 3 detectors make a network. And the idea is they triangulate on the sky where the source is. And so you can say, gravitational wave over there, go look. And so they all have to work together. All 3 detectors have to work together in order to figure out where the source is, like my 2 ears have to work together. Unfortunately, what happened was these gravitational wave detectors are incredibly sensitive instruments. I mean, as we said, you're measuring changes in length that are smaller than a proton. And the real world is a noisy, messy, dirty place. Things glitch, things ping. There's all these complicated control loops that keep the detectors stable. And what happened on the morning of August 17th when we detected the binary neutron star is the LIGO Hanford detector, one of the detectors, this computer software that scans continuously for these patterns, these chirp patterns of gravitational waves, looking for these signals in the detector data. And the software that was looking at the Hanford data in Washington State said, I think I've seen something really interesting. You should take a look at this. And it sends out alerts to people's cell phones and emails, and people start to get text messages saying, hey, come and take a look at this. And we looked, and I used to tell my students, when we finally see a binary neutron star signal, it won't be that obvious. We'll be pulling it out the noise. We looked, and it was just obvious. It was just a beautiful signal. I'm like, okay, well, that's clearly, I'm happy to be wrong. So then look, you can see the chirp. There it is. But it was, the computers only found it in the Hanford detector. They didn't find it in Virgo, and they didn't find it in Livingston, which is key to knowing where on the sky that it is. And so this is where the humans come in. This is why people get PhDs and spend many years, many years trying to understand what's going on in these detectors and figuring out what's going on. So the humans came along and said, okay, we have to take over. The computers have failed us. What's going on? And we realized very quickly, a team of people who've dedicated large fractions of their lives to understanding how these detectors work, realized that there was a glitch, what we call a glitch in the Livingston detector. It's like having a scratch on a record or a CD. You're listening to the music, and you suddenly hear a click. And the computers are trained to ignore clicks and pings and things that don't look like gravitational waves. So they said, oh, we're ignoring that. Never mind. No signal there. Nothing to see here. So the humans actually went in and said, no, look, we can see a signal in Livingston. We can see a signal in Hanford. There's just this giant glitch in Livingston at the same time that the humans can figure out, but the computers couldn't. So what we did is we leapt into action, understood where the glitch came from. This is kind of a frenzied maybe 4 or 5 hours on that morning, trying to figure out what had gone wrong in the instrument, how to remove this, excise it from the detector data, reanalyze the data together with Virgo and Hanford and Livingston, bring the data from all 3 detectors together to then finally triangulate the source and say it's there, and send an email out to the observing community to say, here's the patch on the sky where we think this signal is, go point the telescopes. And fortunately, we managed to do that quickly enough that we didn't really lose that much. I think if we'd moved very, very quickly telescopes in South Africa, it would have been overhead in South Africa, and we could have caught some very important information from the early part of the signal. So next time we're going to do this better, but we got pretty much everything you could hope
Vicky,
for.
you wanted to say something.
Yeah, I
please.
wanted to say that we were, as you said, we were a little lucky because it took 4 or 5 hours, but these early 4 or 5 hours, the source was in the southern sky, and those early 4 or 5 hours was daylight in the south. So even if we had the early localization, it was still daylight, even in southern South Africa. So we were still delayed by a little bit, but we didn't miss the whole day. We missed only maybe a few hours at the end of the day.
Yeah.
So it could have been worse.
So can you imagine, here is an event that was perhaps the most exciting scientific event in the almost history of humankind, and you had a glitch at one of the sites of the experiments. I mean, this is how science works.
But humans saved the day.
Yes, 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 yes. So anyhow, I want to thank this wonderful panel, so please join me.